it's important to begin with a few definitions. Semantics is all about meaning, the meaning of a word, a phrase, a sentence, or a piece of text. This is often confused with syntax, which has to do with the arrangement of words and phrases and is dependent on language. So you can see that there could be two sentences, either in the same language or in different languages, that have the same meaning. Another related word that can cause some confusion is morphology, which has to do with the form of words, the parts of speech, and so forth. And you'll often find this referred to when looking at text mining or auto-categorization software. Mapping is the connection or the ability to try to make connections between the semantics or the concepts in one semantic resource to another. And if you've been on previous calls about the foundational infrastructure and the semantic aspects of that, the semantic management, you may recall that there is an emphasis there on actually storing and making an interface that makes it easy to do this kind of mapping between two semantic resources. Finally, a word that I think is used and abused is ontology, which is some kind of a formal expression of the knowledge of a particular domain, and the scope of that domain can range from a project to a particular discipline in science. There have also been attempts to do, essentially worldwide, global ontologies of all the world's knowledge. So why does meaning matter? Why should we even care about semantics? Well, this is the slide that I call a rose by any other name. And so in our minds, we hold the concept of a rose in this case, which is based on our experience or the perception that we have of the object in the real world. And obviously, if you've never seen a rose, you wouldn't have the experience of it, and it would be very difficult to convey that concept. I think that's important when you start talking about citizen science or about moving from one domain of science to another. In order to communicate, we use words in a variety of languages. We can paint pictures or we use clip art, which stand for both the object in the real world and the concept that we have in our mind. So meaning matters because it's how we convey our understanding of the real world to others. So it's only through our ability to symbolize through words or through images that we can actually communicate when we don't have the object in front of us. However, as I've shown here, and unfortunately my animations won't work in this presentation style, but there can be disconnects at various points in this process. The disconnects can also occur at different stages of knowledge management or the information management process. During discovery, we may be looking in the wrong place for the information that we want. When we select the data or information, we may extract too much or not the right data. When we transform the data for use, we may use invalid conversions, which result in a loss of meaning. And finally, during the analysis phase, all of these disconnects can kind of build up and result in misinterpretation or misuse. And of course, all of these phases where disconnects can happen are further complicated when you're trying to integrate across disciplines, across environmental media, or to integrate across models. In terms of disciplines, the science and higher education, especially in the West, have historically been focused on the concept of disciplines. However, we've seen new disciplines and sub-disciplines arising all the time at the intersection of disciplines, and often that is where real new forms of knowledge and new innovations occur. And even in higher education, there are differences about where such interdisciplinary studies really belong. When dealing with environmental media, air, water, or land, we're dealing with different contexts. And so the same or similar terms can have different meanings. Flow, if you just use that in an unqualified way, it lacks the context of whether you're talking about water or air. Of course, agencies and enterprises have their own terminology. This is pretty apparent to anyone who has gone from one organization to another, even in the same industry. Projects may have their own terms and definitions. Fortunately, humans are very good, or basically very good, at disambiguating meaning. They learn from context and they engage in conversation with one another, and that communication process is where we disambiguate our meaning. However, computers are not there yet, and they need help. One of the ways that we try to help is in the process of developing science frameworks, and we do this for a number of different reasons. But part of the process of developing these frameworks can actually be used to facilitate the computerization or automation of semantics. These frameworks are being developed in many scientific disciplines, especially those where some of the interdisciplinary topics are becoming more mainstream. The sample here that I show is exposure science. And so we find that often the entities or the objects occur in multiple frameworks, but the relationships between those objects are different. For example, a framework for exposure science will include humans in the role of the object being exposed, while in an ecosystem science framework, they might be just one of many species that is in existence in the ecosystem, or they may actually be a negative actor if that framework deals with sources of pollution. So the same entities can occur, but the relationships are different, and therefore the framework helps to set the context for the meaning. So frameworks, models, and databases are specific to a particular problem. The tables and columns in databases or the objects in are related to concepts. They include concepts. These concepts can be referred to using one or more terms. So a semantic resource helps to define and manage the concepts used in a model, or it seeks to reduce the number of different terms that are used to refer to a concept. So you may have a semantic resource that is actually a controlled vocabulary that dictates what can be used in that particular instance. In other cases, it's simply accumulating the concepts and seeking to define them. So in addition to reducing the number of different terms that are used for a concept, the semantic network of concepts and terms can also support the navigation. It can help to mediate meaning. You see this often when you're dealing with Google search, for example, where it will provide you with a did you mean, or you have the ability to in other search systems to look at clustering that has occurred of your results, all of that helps to disambiguate because the terms may actually refer to more than one concept. So it helps to mediate meaning, especially when others are trying to discover or to use the database or the model. In addition, semantic resources can store important properties for an object that differ in context. Here's a great example, thanks to Steve Browdy for this one. I really like this. So both physical oceanography and meteorology use the term sea surface temperature. The definitions are very similar, as you can see here, but from the standpoint of interoperability, there's an important aspect here, and that has to do with the property, the depth of the measurement, which differs widely between the two uses. So these differences are important for making data interoperable, especially if you're dealing with it in an automated fashion or trying to integrate models. So we've talked a little bit about what semantic resources do, what semantics means. There are a wide variety of semantic resources, and thanks to my colleague Marcia Zhang at Kent State University, we have a very, very nice continuum here that she presents. And so down to the left are those resources that are very flat, meaning they are basically termless and have very little relationship between the terms and the concepts. As you move up in terms of complexity to multiple dimensions and over to the right, they get increasingly more functional and also increasingly more complex. They're dealing with relationships. They become more toward the definition of an ontology, which is really a formal definition or formal expression of the entities and the relationships among them in a particular domain. I'm going to focus a bit here on semantic networks and just a little bit on ontologies. So one of the places where the concept of a semantic network is shown is with this whole concept of the linked open data cloud. Linked open data is significant to data interoperability. I'm having trouble with interoperability this morning. I don't know why. This is a recent diagram showing the published linked open data that's been harvested from the web. And there's 2014, and it was done back in 2011, and there has been an increase in the amount. And this isn't intended to be something that is readable, but if you go to this, you can actually see a very interesting report that analyzes the growth of the cloud, the uptake of best practices in this area, and which sectors, which industries are using it. The linked open data and linked data in an enterprise environment is based on the concept of resource description framework, and this is a family of W3C standards for data interchange on the web. RDF uses URIs for the object, so it has to be findable on the web and uniquely identifiable. And it also uses URIs for the relationships. So these three URIs are known as a triple, so you have the right object and the left object and the relationship in between. They can be grouped together as repositories called triple stores. And while the use of RDF and linked data is growing, the open cloud probably hasn't grown as quickly as was originally anticipated. There are a couple of reasons for this. RDF and the concepts of linked data are increasingly used in enterprises, but they're not in an open, published environment. The open use really requires community involvement, and of course that you'll see in a later slide that that's really what GENON is about. So we want to take these concepts, the management of semantics, the mapping of semantic resources, and use community engagement to put out a resource that is bigger than we could do individually. There's a heavy use of the concept of resource description framework and of linked data in certain areas such as social networks. It's obviously very germane to social networks where friend of a friend is used, and also has had a fairly great uptake within libraries, where linking and sharing are really core principles, and so they were early adopters of linked data. And you will see that there are, if you go to the actual cloud and look at it in more detail, you'll see that there are a lot of linked data published by national libraries, the Library of Congress, the Bibliothèque Nationale, and so forth. Moving to ontologies, which is up in the far right in terms of complexity. Here we're talking about the use of formal to identify the relationships. The most formal will have constraints, they'll have rules and axioms, and this really is intended to provide enough information around the relationships and around these things themselves to make them actionable by a computer. They're generally expressed in OWL, though one of the issues is that there are many flavors of OWL, which can make the integration of these ontologies much more difficult. There have been many formal ontologies built in biomedicine, for pharmaceutical development, for engineering, and many other scientific and other disciplines in business as well. While they're becoming more broadly applicable, the most successful still seem to be those that are very focused on a specific project or on an enterprise. And here I should say that you will find often that the word ontology gets used for almost anything along the semantic resource continuum that I showed earlier. However, here we're really talking about very formal ontology and not just any one of the other less formal expressions. So we have semantic resources on that semantic resource continuum, all the way from keyword lists and glossaries to semantic networks and ontologies. But there are other ways that we can provide semantics for data. Another significant resource is the registration of metadata schemes. Metadata can be applied and should be applied, in my opinion, at various data levels, all the way from data dictionaries and table columns, to the collection in the system. And these metadata at various levels support different types of discovery, access, and reuse. One of the things, though, that I think is very important to remember is that metadata scheme is only one level of the semantics that metadata to define and share the metadata tags, but also to share the content guidelines and rules. And often that means pointing to another semantic resource, whether it's a keyword list, a pick list, an ontology, or something in between on the continuum. So throughout this presentation, I've described the importance of applying and managing semantic resources to improve the meaning of data in support of discovery, access, reuse, and ultimately interoperability. At the U.S. Environmental Protection Agency, IIA is supporting the development and maintenance of a variety of semantic resources. These are just a few, and they are really, the ones that we are involved in. Certainly, there are programs and projects and individual researchers within the agency that are doing many, many others, including the development of ontologies and, of course, pick lists and content, metadata content that help to describe their data. This slide represents enterprise-wide resources that are promoted as standards for the agency. Increasingly, we're working not only on these individual resources, for example, maintaining the chemical substance registry or the regulated biological organisms that are in there as well, but we're looking to see how we can use web services and linked data pilot projects and other types of applications to be able to bring these together, collecting and managing the terminology, and semantics is at the center of all of what we are doing here. And we look forward, I think, Bill will second this as well, we look forward to being able to share out what we've done as part of the global network of networks. However, all of this said, while semantics and meaning is important, it is not a silver bullet. There's a lot of requirements, a lot of work to get from where we are to where we're going. Tools are needed for managing, mapping, publishing, and discovering semantics, both resources and down at the individual level. Semantic content must have some common level of expression to be useful in a global environment. For that, we want to provide some reference implementations and some common semantic resources, but we want to keep the barrier for contributing to the whole as low as possible. I think most important is community engagement, commitment to sharing not only the data, but the semantics and the mappings that have resulted from previous interoperability projects and the reuse of data from other sources. In other words, we need a federated, shared semantic environment, which is what educational infrastructure is all about. Here's my contact information, and I look forward to hearing from any and all of you.